All right, time to get those neurons firing up again. We are diving deep into the world of neural networks today, specifically the perceptron model. And wow, you've provided us with some seriously intense notes and diagrams here. It seems like you've been putting in the work.
It's a really comprehensive overview of the perceptron, that's for sure.
But no worries, we'll break it all down together.
It's definitely a foundational concept, this perceptron, in AI and machine learning, and our goal today is to make it all crystal clear for ya.
Sounds good to me. So I'm looking at this first page here, labeled perceptron.pdf. And it says that a perceptron basically boils down to making yes or no decisions.
Exactly.
So it's like a binary decision maker, but how does it actually, work?
Well, you can think of it like deciding whether or not to wear a jacket. You might consider the temperature outside, or the wind, or if it's raining, right?
Yeah, for sure.
A perceptron does something very similar. It weighs different inputs, just like those weather factors, to ultimately arrive at a decision.
Okay, so far so good. My notes also mention these nodes that are all connected together.
Yes,
And each node has a weight assigned to it, which sounds super important.
it is. Think of the weights as a measure of influence. So the higher the weight, the more important that input is to the final decision.
Oh, okay, I get it. So, if it's super cold outside, the temperature input would have a higher weight than, let's say, a light breeze when deciding on that jacket, right?
Exactly. You got it.
All right, starting to see the logic here. But then my notes get into this, formula. It's all about multiplying weights and inputs. What's the math behind all this perceptron magic?
Well, that formula you're looking at, that calculates what we call the weighted sum of all the inputs. You can think of it as each input shouting out its value, but the weights kind of control how loud each voice is.
Interesting.
So then this weighted sum is fed through what we call an activation function.
Activation function. That sounds pretty intense. My notes have a few types listed out, like sigmoid and ton. What are those all about?
So think of the activation function like a gatekeeper. It takes that weighted sum and decides whether it's strong enough to actually trigger an output, like deciding if those combined weather factors actually warrant grabbing your jacket.
Okay.
Sigmoid and tan are just different ways of making that decision, essentially squashing the output between certain values.
Okay, so the activation function is like the final judge, making the yes or no call. Now, I'm also seeing something about different types of perceptrons here. What's the difference between a single layer and a multi-layer perceptron?
Right, so think of a single-layer perceptron like a very simple sorting machine. Maybe it's separating marbles by color.
Okay, yeah.
But what if you wanted to sort by color and size? Well, that's where multi-layer perceptrons, or MLPs, come in. They're like advanced sorting machines with extra compartments to handle much more complex tasks.
So single layer is basic, and multi-layer is like a whole sorting factory. What's really blowing my mind here is this idea of a perceptron learning. It's not just crunching numbers, it's adapting, right?
Absolutely. Perceptrons learn by adjusting those weights and biases that we talked about, and they do this based on training data.
Okay.
It's kind of like practicing a skill. The more you train, the better you get, right?
Oh, yeah.
The goal is to minimize those errors and become super accurate at classifying things.
Makes sense. My notes mention these supervised learning algorithms, like the delta rule. So it's like the perceptron has a coach guiding its training.
Exactly. In supervised learning, we're feeding the perceptron labeled examples, basically telling it what's what. You can think of it like showing it pictures of cats and dogs and saying, this is a cat, this is a dog. Over time, it learns to distinguish them on its own, just like you would.
That's amazing. But hold on, I'm also seeing a whole section here dedicated to the limitations of the perceptron. What's the catch? If they're so smart, why the limitations?
Well, a single-layer perceptron has a big one. They can only really handle problems that are what we call linearly separable. Think of it like trying to draw a single line on a graph to separate two groups of data points.
Okay.
If you can't separate them perfectly with a straight line, the perceptron is going to struggle.
Wait, so a single-layer perceptron can't even tell a cat from a dog if they're too close together on a graph. Seems pretty limited.
It can be, yes. Imagine trying to separate sand from pebbles, but you only have a sieve with big holes. Sometime you need a more sophisticated tool to make finer distinctions. That's where those multi-layer perceptrons with their extra layers can really shine.
Aha, so MLPs are the key to solving those more complex, non-linear problems. My notes have a whole section dedicated to them.
MLPs are definitely a huge leap forward, allowing us to move beyond simple yes or no decisions. They can model much more nuanced relationships, just like in the real world.
Now, this is getting exciting, but I have to admit, flipping through these pages, I'm seeing some pretty intense terms here, like backpropagation and gradient descent.
Right.
Can you demystify those for us a bit?
Sure. Those are the secret sauce to train in MLPs. Backpropagation is essentially a feedback loop, and it helps the network learn from its mistakes, and then ultimately adjust its weights to get better at classifying things.
So it's like the network is doing its own self-assessment, figure out where it went wrong and making adjustments. What about gradient descent, though?
Gradient descent is the process that helps us find the optimal weights for the network. Remember that valley analogy?
Yeah.
Gradient descent is like taking small steps downhill, following the steepest path until we reach the lowest point where the error is minimized.
So backpropagation identifies the problematic weights, and gradient descent guides us towards the best possible values for those weights. It's like a team effort to improve the network's performance.
Exactly.
And my notes mention that this whole process happens iteratively, meaning we do it over and over again.
You got it. It's not a one-time fix. We feed the network data, calculate the error, adjust the weights using backpropagation and gradient descent, and then just repeat the process. Each iteration helps the network get closer to making accurate predictions.
It's like practicing a skill until you master it. The more you practice, the better you get.
That's a great way to put it. And that's really the essence of how neural networks learn, through this iterative process of feedback, adjustment, and refinement.
All right, so we've covered the basic structure of the perceptron, talked about the intricacies of MLPs and their training. It's amazing how all these pieces fit together. But before we get too far ahead of ourselves, let's take a closer look at those activation functions and what makes them so crucial for these powerful neural networks. So we've been talking about these activation functions and how they're like gatekeepers in the neural network. And my notes here list out a whole bunch: sigmoid, tan, softmax, ELU. It's a lot to process.
Yeah, it might seem a bit daunting at first, but each activation function brings something unique to the table. Essentially, they introduce what we call nonlinearity into the network. And this gives it the flexibility to model much more complex patterns.
Okay, nonlinearity, that sounds kind of technical. Can you break that down for us a bit?
Sure, imagine you're drawing a curve on a graph. A straight line is linear, a curve is nonlinear. Without activation functions, our neural network could only model relationships that are straight lines, and that's it.
Oh, so activation functions add those curves, allow the network to handle those more intricate patterns and relationships that we see in real life.
Exactly. It's like the difference between drawing a stick figure and a realistic portrait. You need those curves and details to capture the complexity of, well, anything, really.
That's a great analogy. So let's talk specifics. What's the deal with sigmoid and tan? They seem to pop up a lot in my notes.
Right, so both sigmoid and tan are what we call squashing functions. Basically, they take any input and kind of squeeze it into a specific range. Sigmoid squashes the output between 0 and 1, while tan squashes it between -1 and 1.
So they're like what? Volume knobs, controlling the strength of the signal passing through?
Yeah, you can think of it that way. They help regulate the flow of information within the network, making sure that signals don't get too strong or too weak.
And my notes mention that sigmoid is particularly useful for problems involving probabilities. Why is that?
Well, that's because its output range, 0 to 1, perfectly represents probabilities. For example, imagine we're building a perceptron to predict whether an email is spam. The sigmoid output could represent the probability that the email is spam, with 1 being definitely spam and 0 being definitely not spam.
That makes perfect sense. So it's like the network has given us a confidence level for its decision. Now, what about softmax? My notes say it's used in multi-class classification problems.
Right, so softmax is great when you have more than 2 categories to choose from. Instead of just a simple yes or no, imagine you have options like cat, dog, or bird. So softmax would actually give you a probability distribution across all those categories so you can see which one is most likely.
Oh, so it's like the network saying, I'm 80% sure it's a cat, 15% sure it's a dog, and 5% sure it's a bird.
Exactly. It gives you a much more nuanced understanding of the network's prediction. And finally, we have ReLU, which stands for Rectified Linear Unit.
ReLU, I see that one all over my notes, especially in the context of deep learning.
Right. ReLU is a really popular choice these days because it's quite simple and computationally efficient. It's like a switch that basically turns on when the input is positive and stays off when it's negative.
So it only activates when the signal's strong enough to pass through.
Yep, you got it. And its simplicity makes it much easier to train those deep neural networks with many, many layers.
Okay, so we've got sigmoid and tan for squashing outputs, softmax for multi-class problems, and ReLU for its simplicity and efficiency in deep learning. It's like we've unlocked a whole toolbox of activation functions here.
Exactly. Each activation function has its own strengths and weaknesses, and choosing the right one depends on the specific problem that you're trying to solve. It's part of the art of designing neural networks.
I could definitely see how selecting the right activation function can make a big difference in a network's performance. But all this talk about theories making me crave a more concrete example. Do you think we could walk through a practical scenario just to see how these activation functions actually work in action?
Absolutely, yeah. Let's imagine that we're training a neural network to recognize handwritten digits, like those squiggly numbers you might see on an envelope.
Okay, yeah, that's relatable. We've all seen those numbers that are sometimes hard to decipher.
Right. So we feed the network images of these handwritten